Tonight, on Space Science, the warning does not begin with thunder. It begins high above the continent, where cold northern air, Pacific moisture, and powerful winds in the upper atmosphere are slowly arranging themselves into one vast and dangerous pattern. Before the first roads flood, before the first hail falls, before the first sirens sound, meteorologists are already watching something take shape across the United States. If this kind of deep atmospheric story is worth following, please like the video, subscribe to Space Science, and stay with the channel as the forecast moves from the widest sky to the smallest storm. The story begins far above towns, fields, highways, and coastlines, in the broad moving shell of air that surrounds North America and the nearby oceans. In this outer setting, the United States sits between strong contrasts that are normal to the planet in spring. To the south lies a reservoir of warmth over lower latitudes and warm water. To the north lies colder air that still forms easily over Canada and the Arctic. Between them, the atmosphere does not rest. It shifts, bends, and rearranges itself from day to day. Meteorologists watch this wide arrangement first, because every rain band, every gusty wind, every late snow, and every severe storm at the ground begins as part of this larger circulation. Earth turns steadily beneath the sun, and that turning shapes the motion of air on the scale of continents. The planet also receives sunlight unevenly. Lower latitudes gain more energy, while polar regions gain less. The atmosphere responds by moving heat from warmer places toward colder ones. It does not do this in a straight line or in a smooth and silent sheet. It does it through waves, streams, and broad zones of rising and sinking air. Over North America, those motions often become especially changeable in spring, when the seasonal balance is still shifting. Winter cold has not fully withdrawn from the north, yet increasing sunlight is warming land and water farther south. The result is an atmosphere with strong contrast still available, and contrasts are the raw material from which active weather forms. From space, the continent appears as a complex surface beneath this moving air. Snow may still linger in some northern regions, while forests, plains, desert, and coastline warm at different rates. Mountains redirect wind. Large water bodies slow temperature changes. Dry land heats and cools faster than ocean water. These differences matter, but at the outermost level the atmosphere first responds to something even broader. The pattern of pressure spread across thousands of kilometers. Air tends to move from regions of higher pressure toward regions of lower pressure, but Earth's rotation bends that motion. The result is not simple inward or outward flow. Instead, the air often curves and organizes into vast swirls and long corridors of movement that can extend across much of a continent. Meteorologists call pressure the weight of the air above a place. That weight changes as air warms, cools, rises, sinks, or gathers in one region instead of another. Warm air is generally less dense, which means it tends to expand and rise. Colder air is generally denser, which means it tends to settle. When this happens over very large areas, the broad weather pattern begins to take shape. A region of lower pressure often marks an area where air is rising, cooling, and helping clouds form. A region of higher pressure often marks an area where air is sinking, drying, and limiting cloud growth. In the most general view, the present warning for the United States is not about a single cloud or a single storm. It is about a continental arrangement in which these large areas are becoming aligned in ways that support active weather over many states at once. The outer atmosphere above North America rarely moves as one uniform mass. It separates into air masses, large bodies of air that carry similar temperature and moisture over wide distances. Some form over cold land and remain dry and cool. Some form over warmer water and carry moisture. Some are mild, some sharp, some heavy with humidity, and some thin and dry. When these different air masses are spread across the map, the country becomes a zone of meeting and contrast. The southern and central United States often stand near one of the most active meeting grounds on Earth, because warm moist air from lower latitudes can travel northward, while colder drier air pushes southward from the interior of Canada. The planet does not need to create unusual physics for dangerous weather. It only needs to place unlike air masses close enough together and provide the larger circulation that brings them into contact. At this outer level, meteorologists are not yet watching a thunderstorm over a town or a flood in a river valley. They are watching the atmosphere as a connected system. Satellite images reveal cloud shields stretched across several states or over long reaches of ocean. Pressure maps show centers and gradients, meaning the rate at which pressure changes from one place to another. A strong gradient often points to stronger wind, because the atmosphere is trying to rebalance the difference. Temperature maps reveal sharp boundaries where warmth and cold lie close together. Moisture fields show where the air contains enough water vapor to feed cloud formation. None of these alone guarantees severe weather. Together, they describe whether the continental stage is being set for it. This is why warnings often begin before skies darken in a given location. The broad pattern can already show that energy, moisture, lift, and wind are becoming organized on a large scale. In meteorology, lift means any process that causes air to rise. Rising air cools. Cooler air can no longer hold the same amount of water vapor, so that vapor begins to condense into tiny droplets or ice crystals. Clouds form. If the rising continues and moisture remains available, precipitation may follow. In the outermost view, the warning signs are therefore not dramatic in themselves. They are structural. They appear in maps, model guidance, pressure fields, satellite loops, and upper air observations. They show an atmosphere arranging itself into a state that is more supportive of widespread impact. The United States is especially exposed to this kind of large-scale arrangement because of its geography. Mountain barriers are strong in the west, but the central part of the continent is relatively open from north to south. This openness allows cold air to move southward with fewer obstacles, and warm air to move northward with similar ease. Few continental settings allow such direct exchange over such a long distance. As these air masses shift, the broad atmospheric pattern can quickly become one of tension and movement. What appears calm in one region may already be connected to a stronger change forming far away. A dry plain may soon sit beneath faster winds. A quiet, warm sector may already be linked to moisture transport. A cold region may already be part of a developing boundary. At the outer scale, everything belongs to one circulation. Even the timing of daylight contributes quietly to the pattern. Spring sunlight strengthens daytime heating over land, especially across the southern states and interior plains. Yet the atmosphere above may still carry winter-like characteristics farther north. This uneven seasonal transition helps preserve strong temperature differences across distance. Those differences increase what meteorologists call instability and baroclinicity. Instability refers to an atmosphere that encourages rising motion once air is lifted. Baroclinicity refers to a state in which temperature changes strongly across space, helping storms grow and organize. These are not rare ideas reserved for unusual years. They are part of the normal language of spring weather, and they help explain why broad warnings can emerge over the nation even before the finer details are known. So the first region of the story is not a state, a city, or a storm cloud. It is the planetary and continental shell of air in motion, carrying heat, cold, moisture, dryness, rising zones, sinking zones, and strong boundaries across North America. Meteorologists begin here because this is where the country's coming weather first exists as possibility made visible in pattern. The warning is born in scale, in contrast, and in the slow but relentless reshaping of the atmosphere above the land. Beyond the United States, beyond the line of coastal cities and inland plains, the atmosphere continues to gather and sort its ingredients over the ocean and the far northern land. In this second region, the broad pattern is shaped by two main sources feeding the continent from outside its own borders. One comes from the Pacific, where moist marine air and travelling disturbances approach North America from the west. The other comes from Canada and the Arctic, where colder, denser air can collect over snow, ice, and long nights of recent winter and then begin to move southward. Meteorologists watch these two sources with care because they help define the outer boundaries of what is heading toward the United States before the air ever reaches the central forecast area. Over the Pacific Ocean, the atmosphere behaves differently from the way it behaves over land. Water changes temperature more slowly than soil or rock. It stores heat deeply, releases it gradually, and keeps the lower atmosphere above it from swinging as sharply between day and night or from week to week. This often gives marine air a steadier character. It may be cool, mild, or relatively moist, depending on where it forms and how far it travels, but it usually carries the influence of the ocean in its temperature and humidity. When disturbances move across the Pacific, they often draw from this moisture. They do not always arrive at the west coast as violent storms. Sometimes they come as long cloud bands, broad waves of lower pressure, or strong belts of wind that prepare the atmosphere for later developments inland. The Pacific itself is not one single source of air. It contains colder northern waters, milder middle latitudes, and connections to subtropical moisture farther south. The atmosphere flowing over these waters can change as it travels. A parcel of air is a small imagined piece of the atmosphere that meteorologists use to describe motion and change. As a parcel moves over colder water, it may cool and become more stable, meaning less willing to rise. As it moves over milder water or along a strong wind corridor, it may gather moisture and become part of a larger cloud system. By the time such air approaches the western edge of North America, it may already be carrying layers of cloud, broad rising motion, and the early shape of a developing weather system. When this marine influence reaches the mountains of the west, some of its moisture may be forced upward by terrain. This process is simple in idea. Air cannot pass through a mountain range, so it is lifted as it moves over higher ground. Lifting cools the air. Cooling encourages condensation. Clouds may thicken, and rain or snow may form. Yet even before that happens, the Pacific influence has already done something important on the outer scale. It has delivered moisture, momentum, and moving disturbances toward the continent. These disturbances may later help deepen pressure systems, strengthen temperature contrasts, or align with air arriving from the north. In that sense, the Pacific acts not only as a supplier of moisture but also as a conveyor of atmospheric structure. Far to the north, a different kind of source region forms. Over Canada and the Arctic, the land and lower atmosphere cool efficiently, especially through the colder half of the year. Even as spring advances, some of that cold reserve remains. Snow cover reflects sunlight. Ice and cold ground slow warming. Long stretches of northern interior land allow dense air to build and remain coherent over large distances. This air is usually drier than air from warmer oceanic regions because colder air holds less water vapor. It is also heavier, which means it tends to stay close to the surface and can move outward when the larger circulation permits. Meteorologists often describe this as a polar or Arctic air mass, depending on its origin and character. What matters most at this outer stage is not the exact label, but the contrast it brings, compared with air moving northward from warmer latitudes. This northern air is colder, denser, and often clearer at first. Its leading edge can mark a sharp zone of change in temperature, pressure, and wind direction. Yet before it becomes a front over the United States, it exists as a reservoir spreading and shifting over the northern part of the continent. Forecast models track how deep it is, how fast it's moving, and whether it is likely to remain intact as it travels south. The meeting between Pacific influence and polar influence does not happen at one fixed line. It depends on the broader circulation and on where the atmosphere chooses to arrange its waves. At times, marine air pushes inland first, laying cloud and moisture across the west before colder air drops south and undercuts it. At other times, cold air advances earlier and creates a sharper contrast when Pacific moisture later arrives overhead. The order matters because the atmosphere responds differently depending on which ingredient arrives first. But in this second region of the story, the important point is simpler. The United States is not generating its weather in isolation. It is receiving upstream signals from ocean and from far northern land. And those signals help determine what kind of pattern will form farther in. Cold air from Canada does not need to be exceptionally rare to become important. Its power lies in its density and persistence. Because it is heavier, it can slide beneath milder air and help lift that air upward. It can also spread rapidly through open terrain, especially east of the Rocky Mountains, where the central part of the continent offers fewer barriers to north-south movement. At the same time, Pacific disturbances aloft may continue moving eastward, adding cloud cover, wind energy, and broader lifting mechanisms. When the two influences begin to align, the atmosphere acquires stronger gradients. A gradient is a change across distance. In weather, stronger gradients in temperature or pressure often mean stronger forcing, meaning stronger reasons for the atmosphere to move and reorganize. Satellite imagery often reveals these outer influences clearly. Over the Pacific, long cloud plumes may arc toward the west coast, while farther north, colder dry air may appear as broad, clearer regions behind cloud systems or beneath sinking motion. Upper air observations and computer models help show where the colder dome of northern air is thickest and where the moist marine stream is strongest. Meteorologists compare these fields not because they expect every offshore cloud band or every northern chill to become dangerous, but because the overlap of these features can signal that the larger pattern is becoming more efficient at producing significant weather downstream. The ocean contributes patience and moisture. The north contributes density and cold. Neither acts alone for long over North America. Their importance lies in how they enter the same continental system from opposite directions and begin to define its edges. One outlines the moist and moving boundary from the west. The other outlines the colder and heavier boundary from the north. Between them, the atmosphere over the United States becomes a zone ready for sharper contrasts, stronger lift, and more organized change. That is why meteorologists begin watching what is heading for the country well before the country itself becomes the main stage. The outer pattern is already arriving through these upstream flows, one from open water, one from high-latitude land, each carrying its own physical character into the same developing map. High above the continent, above the mountains, plains, rivers, and coastlines, a narrow but powerful current of air moves from west to east. Meteorologists call it the jet stream. It is not a river in the ordinary sense, But the comparison is useful because it helps describe a concentrated flow moving within a broader surrounding medium. In the upper troposphere, the lowest major layer of the atmosphere where most weather forms, the jet stream marks a zone where wind speeds become much stronger than the air around them. It does not blow in one perfectly straight line. It curves, dips, narrows, and widens, tracing a shifting path that helps decide where storms travel, where air rises, and where calmer weather settles. The jet stream forms because of strong temperature differences across distance. When cold polar air lies north of warmer air, the atmosphere between them develops a contrast in thickness and pressure with height. Air pressure decreases with altitude, but it does not decrease in exactly the same way everywhere. Warmer air expands, so pressure surfaces stand higher above warm regions. Colder air contracts, so the same pressure surfaces sit lower above cold regions. This creates a slope in the upper atmosphere. Air responds by accelerating along that slope, while Earth's rotation bends the motion into a strong west to east flow. In simple terms, the jet stream is one of the atmosphere's great balancing mechanisms. It is born from contrast, and it carries that contrast across the map. Because the United States often lies beneath or near a strong spring temperature boundary, the country is frequently influenced by this high-altitude current. Meteorologists watch it closely because the jet stream is more than a belt of fast wind. It is also a guide for weather systems. Regions beneath it may experience stronger upper-level support for clouds and storms, while regions far from it may lie under gentler conditions. The exact placement matters. A shift of even a few hundred kilometers can change whether a particular state lies beneath stronger rising motion or beneath sinking, drying air. The path of the jet stream often resembles a wavering line with broad bends. Some parts arch northward, others dip southward. These bends are called ridges and troughs, though at this stage it is enough to understand them as large undulations in the flow. When the current bends, the speed of the air also changes from place to place. Faster segments may enter or leave slower ones. As this happens, the atmosphere above different regions can either spread apart or come together. When air aloft spreads apart, lower air tends to rise to replace it. This process encourages cloud formation and the development of surface low pressure. When air aloft comes together, the air often sinks beneath it, warming and drying as it descends. In this way, the jet stream helps determine where the atmosphere is more likely to deepen a weather system and where it is more likely to suppress one. The current itself usually lies several kilometers above the ground, far above the height of ordinary buildings and well above the level of low clouds. People below may not sense it directly, yet its influence reaches downward through the whole depth of the weather pattern. A storm at the surface often becomes stronger when the upper flow is arranged to remove air from above it. This removal lowers the pressure beneath and encourages more air to converge and rise from below. The process sounds abstract, but it is one of the central links between the fast winds aloft and the conditions people later experience as rain, gusts, and falling pressure. In spring, the jet stream over North America often remains active because the seasonal contrast between north and south is still substantial. Summer usually brings a weaker temperature boundary across much of the continent, but spring often keeps that boundary alive while increasing daytime warmth over the southern and central states. The upper flow, therefore, remains capable of transporting disturbances rapidly and of sharpening the difference between active and quiet regions. Meteorologists track these upper-level waves using weather balloons, aircraft observations, satellites, and numerical models. They study not only where the jet stream is strongest, but how its shape is changing hour by hour. A slight deepening in one bend or a subtle acceleration in one segment may help explain why a broad cloud shield expands or why a pressure system begins to intensify. The jet stream also acts as a kind of corridor for embedded disturbances. These are smaller ripples moving within the larger current, each capable of adding lift, turning the wind with height, and helping weather systems organize. A disturbance does not always appear dramatic on its own. It may only be a kink, a pocket of colder air aloft, or a compact wave of rotation within the larger flow. Yet when such a feature travels along the jet and crosses a region where moisture and temperature contrasts are already present, it can help convert a merely unsettled pattern into a more organized one. In this sense, the jet stream is both the path and the engine room of broad weather development. Meteorologists also pay close attention to wind shear, which means a change in wind speed or direction with height. The jet stream is a major contributor to this. Near the ground, winds may be modest and come from one direction, while high above, much faster winds sweep from another. This layered structure matters because it helps separate rising and sinking air within cloud systems, allowing storms to last longer and organize more efficiently. At the broad scale, however, wind shear first appears not as a property of a single thunderstorm, but as part of the larger upper air design. The jet stream lays out the background environment in which later, smaller features may develop. At times the current flows in a relatively zonal pattern, meaning it runs more directly from west to east with limited waviness. At other times it becomes more amplified, with deeper bends that allow cold air to sink farther south and warm air to build farther north. An amplified pattern often creates stronger regional contrasts, slower movement in some areas, and a greater chance for persistent weather. When meteorologists warn that a significant pattern is taking shape, they are often responding to one of these larger changes in the upper flow. The exact winds cannot be seen with the eye from the ground, yet their arrangement governs much of what later appears visible. So in this third region, the story is carried by a fast river of air above the continent. It is shaped by temperature contrast, bent by planetary rotation, and made important by the way it directs motion below. It does not create every storm by itself, but it helps decide where storms travel, where lifting becomes stronger, and where the atmosphere begins to organize its warnings into reality. At this scale, what is heading toward the United States is not yet a local event. It is a pattern in motion along the high-altitude current that steers the weather from above. As the high-altitude current continues across the continent, it does not remain a simple line of fast wind. It develops broad shapes that guide the atmosphere below. Some parts of the flow bow northward into gentle arches of warmer air aloft. Other parts dip southward as colder air presses deeper into lower latitudes. Meteorologists call these features ridges and troughs. A ridge is an elongated zone of higher pressure aloft, usually linked with warmer air and more sinking motion. A trough is an elongated zone of lower pressure aloft, usually linked with colder air and more rising motion. These are not objects like mountains or walls. They are patterns in the atmosphere's structure, visible on pressure maps and in the height of air layers far above the surface. Yet they are among the most important features in the broad steering pattern that shapes what heads toward the United States. A ridge often forms where the air column is warmer and expanded, because warm air takes up more vertical space. A given pressure level sits at a greater height above the ground. On weather maps made for the upper atmosphere, those higher heights appear as a bulge northward. The winds tend to curve around that bulge. Beneath it, the air often sinks slowly. Sinking air warms as it descends because it encounters greater pressure below. Warmer descending air usually becomes relatively drier, which can limit cloud growth. For that reason, ridges are often linked with quieter weather warmer conditions, and clearer skies over broad areas. Yet even a ridge is not simply calm in every sense. It can steer moisture around its edges, help intensify heat over land, and set sharp boundaries where active weather may organize nearby. A trough behaves differently. It marks a southward dip in the upper flow, usually where the air aloft is colder and more compact. In such a region, the pressure surfaces sit at lower heights. The winds curve through this dip and often carry colder air farther south than it would otherwise reach. The colder air aloft matters because it can make the atmosphere more unstable when the surface below remains relatively warm. Instability is the tendency for lifted air to keep rising once it becomes warmer than its surroundings. A trough can therefore do more than steer weather systems. It can change the background condition of the atmosphere and make rising motion more effective. Beneath and ahead of a trough, cloud formation often becomes easier. Surface pressure may fall, and organized precipitation becomes more likely. Meteorologists pay close attention not only to where a trough or ridge is located, but also to its shape and movement. A broad, shallow trough may support a wide area of unsettled weather without producing especially intense development. A sharper, deeper trough often creates stronger contrasts, stronger winds aloft, and more vigorous lifting. The same is true of ridges. A weak ridge may bring only a temporary reduction in cloud cover. A stronger ridge may build persistent warmth and dryness over a region, and deflect incoming disturbances far to the north or along its flanks. In this way, the broad upper pattern acts like a steering structure. It does not decide every local detail, but it establishes the paths along which colder air, warmer air, and storm energy can travel. The arrangement of troughs and ridges across North America often determines where the main weather corridors will lie. If a trough deepens over the western part of the continent, air ahead of it tends to flow northward over the central and eastern states. That can encourage warmth and moisture to spread into the interior. If a trough advances into the central states, cooler air may sweep into the plains while rising motion expands eastward. If a ridge strengthens over one region, the storm track may bend around it, sending the most active weather along its edge rather than through its center. This is why meteorologists often speak of steering. The atmosphere at these heights behaves like a large moving framework, and the framework directs where lower-level features are most likely to organize and intensify. Within a trough, the winds usually curve in a way that favors spin on a broad scale. In meteorology, that spin is not necessarily a visible whirl, but a tendency for the air to rotate as part of the larger flow. This helps explain why troughs are frequently associated with surface cyclone development, meaning the formation or strengthening of low-pressure systems. Ahead of the trough, upper-level divergence often increases. Divergence means that air spreads apart. When air spreads apart aloft, more air rises from below to replace it. Rising motion can cool and condense moisture, helping cloud fields thicken and precipitation expand. Behind the trough, sinking motion often becomes more common, along with cooler and drier air. So even within one large upper feature, different sectors can support very different surface weather. Ridges also influence the pattern through contrast. Along the western or eastern side of a ridge, winds may accelerate and bend in ways that create transition zones between calmer and more active air. These edges can become important places where fronts sharpen and storms track. A ridge can therefore indirectly support severe weather by storing warmth and helping channel moisture into the region just beyond it. It may seem quiet at its center while contributing to stronger development along its margins. The atmosphere often works this way. One part of the pattern prepares energy or contrast that another part later uses. Spring over the United States is especially sensitive to these upper-level shapes because the seasonal gradients remain strong. A trough digging southward can still tap into late-season cold, while the land beneath increasing sunlight can warm rapidly ahead of it. A ridge can build warmth over the south or east, allowing low-level air to become more buoyant and moisture-rich. When these patterns persist for several days, the effects accumulate. The atmosphere does not reset each morning. Heat can build, soil can moisten, snow can melt, and low-level air can continue changing while the upper pattern remains in place. This persistence is one reason meteorologists become concerned when they see a trough ridge arrangement settling into a favourable position for repeated rounds of active weather. Forecast models attempt to represent these shapes precisely because a small shift in the axis of a trough or ridge can alter the outcome over wide areas. If a trough is farther west, moisture return ahead of it may strengthen over the plains. If it moves east faster than expected, the main storm corridor may shift toward the Mississippi Valley or beyond. If a ridge is stronger than projected, it may block a disturbance longer and slow the advance of cooler air. These are not minor technical details. They help explain why one region may face prolonged rain while another experiences strong dry winds, and why warning areas can expand or contract as the upper pattern evolves. So this fourth region of the story remains high above the ground, but it moves closer to the way the atmosphere begins choosing where its energy will be spent. The broad bends in the flow guide cold and warmth, rising and sinking, cloud growth and temporary clearing. Through troughs and ridges, the upper air draws the first clear routes of the weather to come. What heads toward the United States is therefore not only a mass of air or a moving front, it is a shaped and steering pattern aloft, one that directs the continent's changing conditions with slow, continuous force. Below the shaped flow of the upper atmosphere, the weather begins to acquire clearer form at lower levels. What was first a continental pattern of contrast and steering now becomes visible in the pressure arrangement closer to the ground. Meteorologists study this layer carefully because it is here that the atmosphere starts to gather its broad tendencies into systems that people can more easily recognize on daily weather maps. Areas of low pressure begin to define the main centers of unsettled weather. Areas of high pressure begin to define the quieter regions, or the colder and drier air spreading behind a change. Between them, the pressure gradient sharpens, winds adjust, and the atmosphere prepares the next stage of development over the United States. Pressure at the surface is not simply a number written on a map. It is the result of the entire column of air above a place, and how that column is changing. When air rises from the lower atmosphere and continues upward, some of the weight of that column is effectively reduced near the surface. Pressure falls. When air sinks and accumulates in the lower levels, pressure tends to rise. These changes are often gradual, but they reveal whether the atmosphere is becoming more supportive of cloud growth and storm organization, or more supportive of clearing and stability. A falling pressure pattern can signal that the atmosphere is drawing air inward and upward. A rising pressure pattern often signals spreading colder air, sinking motion, or a stabilizing influence. On surface maps, a low-pressure area usually appears as a center around which the winds curve inward. In the northern hemisphere, that flow tends to rotate counterclockwise because Earth's rotation bends moving air. Yet the motion is not a simple whirlpool. Friction with the ground slows the wind compared with the flow aloft, and that slowing allows some air to angle inward toward the center rather than moving only around it. As the air converges, meaning it comes together, it has nowhere to go except upward. That rising motion helps extend clouds, strengthen precipitation, and maintain the low itself. In this way, a surface low is both a symptom and a driver of organized weather, It reflects the atmosphere's larger structure, but it also helps intensify the very pattern it belongs to. A high-pressure area behaves differently. The air tends to sink from above and spread outward at the surface. In the northern hemisphere, the flow around a high usually curves clockwise. Because the air is descending, it often warms and dries somewhat as it compresses under increasing pressure. That discourages widespread cloud formation, though it does not always eliminate clouds entirely. A strong high can bring calm weather, or it can bring brisk winds if the pressure difference between it and a nearby low becomes large. In colder seasons and transitional periods, a high may also act as a source of dense, cool air that later pushes toward lower latitudes. So while highs are often associated with fair weather, they are also part of the moving structure that defines the edges of change. Meteorologists look closely at isobars, which are lines connecting places of equal pressure. Where these lines crowd together, the gradient is strong. A strong pressure gradient usually produces stronger wind because the atmosphere is trying more urgently to balance the difference between one area and another. Over the United States, this can mean broad zones of gusty wind even outside the heaviest rain or strongest thunderstorms. Wind becomes part of the warning not only when it's produced inside a storm cell, but also when the broader pressure pattern itself tightens across many states. In some cases, long stretches of open terrain allow these stronger winds to spread efficiently, carrying dry air, lifting dust, or driving rough conditions across roads and fields. As the surface pattern takes shape, it also begins to connect more clearly with the upper-level troughs and ridges already in place. A low at the ground often strengthens most effectively when it sits beneath a region of upper-level support, where air is spreading apart aloft and encouraging upward motion from below. When that coupling is strong, pressure can fall more steadily, winds can strengthen around the system, and the weather associated with it can become more organized. If the upper support weakens or moves away, the low may stop deepening and the system may begin to fill, meaning its central pressure rises and its circulation weakens. This connection between upper and lower levels is one of the core reasons meteorologists never study the surface map in isolation. The atmosphere behaves as a layered whole. By this stage, the developing pattern over the United States often begins to show recognizable sectors around a low-pressure system, east or southeast of the center. Milder air may be drawn northward. North of the center, cooler air may hold its ground. West or southwest of the center, winds may shift and drier air may begin to move in. These are still broad regions, not yet the narrow fronts or storm cores that later become more distinct, but their outlines are starting to emerge. A surface low helps collect the atmosphere's ingredients into a more ordered arrangement. It creates zones of inflow, zones of ascent, and zones where cloud and precipitation may become more persistent. The ground itself also influences how clearly the pressure pattern appears. Over mountains, the atmosphere is forced to adjust to terrain, and surface pressure values must be interpreted with care, because height above sea level changes the raw reading. Over the open plains, patterns can appear more cleanly, and the movement of cold or warm air may be easier to detect. Along coastlines, pressure systems can interact with sea breezes, marine layers, and temperature differences between land and ocean. Even so, the broad logic remains the same. Where the surface pressure falls and the surrounding winds begin curving inward, the atmosphere is organizing for active weather. Where pressure rises and air spreads outward, another part of the pattern is establishing its influence. Pressure tendencies, meaning the way pressure changes over several hours, are especially important. A low that remains weak but stationary may bring clouds and rain without much strengthening. A low whose pressure is steadily falling is often becoming more dynamic. especially if upper support and temperature contrast remain favourable. Meteorologists examine these trends because warnings depend not only on what exists at a given moment, but on whether the system is maturing. The atmosphere near the surface often reveals this maturation through subtle but measurable changes in wind shift, pressure fall, and moisture increase. So this fifth region brings the broad atmospheric design down closer to the lived map of the nation. The weather now has centres and gradients. The air is no longer only contrasting in distant source regions or being steered by high-altitude flow. It is beginning to gather into identifiable areas of low and high pressure that will direct wind, lift, cloud formation, and the placement of later boundaries. What is heading for the United States now has clearer shape. It exists as an emerging surface pattern, still broad, still unfolding, but increasingly ready to express the larger forces that have been arranging themselves overhead. Once the pressure pattern begins to organize near the surface, one of the most important ingredients in the developing weather starts moving with greater purpose. This ingredient is moisture, carried as water vapor in the lower atmosphere. It is not yet cloud, rain, or storm. It is the invisible supply from which those forms may later emerge. Over the United States, one of the most reliable warm season and springtime sources of this moisture lies to the south, over the Gulf. Meteorologists watch the return flow from this region with unusual care because it often marks the difference between a merely windy pattern and one capable of producing widespread rain, strong thunderstorms, flooding, and other significant effects. In this sixth region, the story narrows from pressure centres and gradients to the moist air that begins streaming northward into the country. Warm water continually adds moisture to the air above it through evaporation. In evaporation, some water molecules at the surface gain enough energy to escape into the air as vapour. The warmer the water, and the more favourable the wind and temperature conditions, the more readily this exchange can occur. Over the Gulf, the lower atmosphere often becomes both warm and humid. Humidity means the amount of water vapour present in the air. Meteorologists often measure it in several ways, but at its simplest it describes how much invisible moisture the atmosphere is carrying. This matters because water vapour stores latent heat, meaning heat that is hidden within the phase of water and can later be released when vapour condenses into liquid droplets. That release strengthens rising motion in clouds and helps power deep convection, the vertical transport of heat and moisture through vigorous rising air. When a surface low develops over the plains or central part of the country, or when high pressure settles to the east or southeast, the surface winds often begin to draw air northward from the Gulf. This broad northward movement is known as return flow because it often marks the return of maritime tropical air after a previous cool or dry period. The air is maritime because it forms over warm water. It is tropical because it is warm relative to the polar and continental air masses to the north and west. At this stage, the flow may not appear dramatic. It may simply show up as steadily increasing dew points, warmer nights, low cloudiness, or a moist wind from the south. Yet these are some of the clearest signals that the atmosphere is being resupplied with the fuel needed for more active weather. Dew point is one of the most useful measures in this part of the story. It is the temperature to which air must cool for saturation to occur, meaning for it to become full enough of moisture that condensation begins. A higher dew point usually means the air contains more water vapour. Meteorologists value this measure because it reflects actual moisture content better than relative humidity alone. As dew points rise northward through Texas, the lower Mississippi Valley, the southeast, or the Central Plains, the moist sector of the weather system begins to expand. This expansion is quiet but important. The atmosphere near the ground becomes less dry, more buoyant when heated, and more capable of producing cloud and rain once lifting begins. The journey of Gulf moisture northward is not always smooth or uniform. It depends on wind speed, temperature, the presence of older cool air near the surface, and the broader structure of the pressure pattern. Sometimes the moisture remains shallow, concentrated in the lowest 1 or 2 kilometers of the atmosphere. In other cases, stronger southerly winds transport a deeper and richer moist layer well inland. Meteorologists often watch for the development of a low-level jet, which is a corridor of relatively fast wind in the lower atmosphere, usually strongest at night. This current can transport warm moist air northward with surprising efficiency. It is one reason why thunderstorms or heavy rain sometimes intensify after sunset rather than fading. The moist supply does not stop when the sun goes down. In some cases, it becomes more organized. As this moisture spreads inland, it changes the atmosphere in several ways at once. It increases the amount of water available for cloud formation. It reduces how much daytime heating is needed for air parcels to become unstable. It also raises the amount of potential rain that can fall from a storm, since a moisture column can yield more condensation and precipitation. In addition, when moist air is lifted and water vapor condenses, the latent heat released makes the rising air relatively warmer than its surroundings, allowing it to continue climbing. This is one of the key reasons moist air can support stronger thunderstorms than dry air under otherwise similar conditions. The vapor is invisible, but its physical role is enormous. The northward moisture return often reaches different parts of the country in different forms. Near the Gulf Coast, the air may become deeply humid with low cloud decks and warm nights. Farther inland, the first signs may be more subtle, such as a gradual softening of the air, a persistent south wind, or morning stratus, which is a low flat cloud layer. In the plains, the moisture may gather east of a dry boundary, while air farther west remains much drier. In the Mississippi Valley, the humid flow may merge with existing cloud bands and strengthen widespread rain. In the southeast, it may support repeated rounds of showers and storms where the larger pattern already favors lift. Everywhere it travels, it shifts the atmosphere away from dryness and toward readiness. Meteorologists also study how this moist flow interacts with the land surface. Early spring vegetation, bare soil, wet ground, and urban areas each exchange heat and moisture with the atmosphere differently. During the day, strong sunlight can warm the humid air from below and increase instability. At night, the moist layer may cool into fog or low clouds if winds weaken enough, though stronger return flow usually keeps the air mixed and moving. Over the plains and lower valleys, the moisture can spread quickly. Over elevated terrain or regions where cooler air remains trapped near the surface, its advance may be slower or more uneven, but even then, the larger pattern often keeps pushing the humid air northward, deepening the contrast between the moist sector and the colder or drier air nearby. This moisture return is one reason warnings can grow more serious over time even if the visible weather has not yet reached its peak. A pressure system without strong moisture support may produce wind shifts and scattered precipitation. The same system, if fed for many hours by warm, humid air from the Gulf, can become capable of broader heavy rain, stronger storm towers, and more efficient flooding. The fuel enters quietly. It is measured in thermodynamic profiles, dew point maps, and lower atmosphere wind observations rather than in dramatic imagery. Yet without it, much of the later weather would remain weak or disorganized. So in this sixth region, what is heading toward the United States becomes richer at its base. The atmosphere is no longer only shaped by pressure and steered by upper flow. It is being filled with moisture from the south, carried northward as invisible vapor through the lower air. This return flow feeds clouds before they form, strengthens lifting before storms fully rise, and prepares the nation's weather pattern to move from simple structure into greater consequence. As the lower atmosphere fills with moisture from the south and the pressure pattern gains clearer shape, the broad weather system begins to mark itself with boundaries. These boundaries are called fronts. A front is not a line painted across the land, but a transition zone between air masses with different temperature, moisture, and density. On weather maps, it may appear as a narrow curve extending away from a low-pressure center. In the real atmosphere, it is usually a sloping three-dimensional zone that can stretch across several states and rise gradually through the lower and middle levels of the air. In this seventh region, the developing pattern over the United States becomes more defined through these meeting lines, where unlike air masses press against one another and the atmosphere is forced into motion. A cold front forms where colder, denser air advances into warmer air. Because the colder air is heavier, it tends to slide beneath the warmer air near the surface. The warmer air is lifted as the cold air undercuts it. This lifting is one of the simplest and most important processes in weather. Air does not need to rise on its own if a denser air mass is pushing beneath it. Once it rises, it cools. As it cools, water vapor condenses into cloud droplets and sometimes ice crystals. Clouds thicken, precipitation develops, and the front becomes active weather rather than only a thermal boundary. Over the United States, especially in spring, a cold front can extend from the Great Lakes to the southern plains or from the Mississippi Valley toward the Gulf Coast, organizing a long band of changing sky, temperature, and wind. The structure of a cold front depends on the contrast between the air masses and on the speed of the advancing cold air. A strong front with a sharp temperature change may produce a narrow but intense band of uplift. A weaker one may support more scattered showers or a wider region of clouds with less abrupt weather. Behind the front, the air usually becomes cooler and drier. Winds shift, often turning from a southerly or southwesterly direction to a westerly or northwesterly one. Pressure may rise as the denser air spreads in. The sky may clear quickly in some places, or low clouds may linger if the cooler air remains moist and unstable near the ground. At this stage, meteorologists study the front not as a single local event but as a long organized meeting zone whose exact placement can determine where the most active weather forms. A warm front behaves differently. In this case, warmer air advances toward a region of cooler air already in place, because the cooler air is denser and often shallower near the surface. The warmer air usually cannot push it aside directly. Instead, the warm air rises gradually up and over the cooler dome. This creates a gentler slope than the one typically found along a cold front. The lifting may therefore be broader and more layered, producing widespread cloud fields that develop in a more ordered sequence. High thin clouds may appear first, followed by thicker middle clouds, and then lower cloud layers and steadier precipitation as the front draws closer. The result is often less abrupt than a cold frontal passage, but it can cover a broad area and persist for many hours. Warm fronts are common on the northern side of a developing low-pressure system, where moist southern air is attempting to spread northward over cooler surface air. In the central and eastern United States, this can produce large shield-like areas of cloud and rain ahead of the low. Temperatures near the ground may remain cool north of the boundary, even while much milder air is flowing just above. This layered structure matters because it shapes precipitation type, cloud thickness, and the overall character of the weather. The atmosphere does not always change at the same speed from top to bottom. A warm front often reveals that difference clearly, with the warmer air arriving first aloft and only later, if at all, fully replacing the cooler surface air. Some fronts move little for a time. When the opposing air masses push with roughly similar force, the boundary may stall. A stationary front is therefore a front that is no longer advancing quickly in either direction. Yet it is not inactive. It remains a corridor of contrast and uplift. Moist air may continue to flow along it, and weaker waves of the low pressure may travel across it one after another. This can produce repeated rounds of cloud, rain, or thunderstorms over the same region. In the United States, a stalled boundary across the South, Midwest, or Mid-Atlantic can become especially important because it serves as a focus for prolonged rainfall and sharp local differences in temperature and wind. One side of the boundary may feel cool and stable, while the other remains warm and humid only a short distance away. Fronts are also zones of convergence, meaning that air flowing from different directions is brought together. This matters because converging air near the surface increases the need for upward motion. Along a front, the convergence may be strengthened by differences in wind direction between the two air masses. Southerly winds carrying warm, moist air may meet northerly or easterly winds on the cool side. The boundary then becomes both a thermal contrast and dynamic one. Meteorologists often track these wind shifts carefully because they reveal where the frontal zone is truly located, even when clouds and precipitation make the temperature contrast less obvious. The slope of a front through the atmosphere is important as well. A front is not vertical. It tilts, usually toward the colder air. This means the weather associated with it may extend far from the exact surface position of the boundary. Rain from a warm front can occur well north of the surface line because the warm air is already gliding upward over cooler air at higher levels. Likewise, clouds and lifting along a cold front may deepen aloft before the surface wind shift reaches a given town. This three-dimensional structure is one reason fronts can seem to announce themselves in stages: pressure, clouds, wind, and temperature. Each respond according to their place within the sloping boundary. In spring, fronts across the United States often become especially active because the contrast between air masses remains strong while moisture is increasing. Cold air can still arrive from Canada. Warm, moist air can surge northward from the Gulf. The central and eastern parts of the country offer broad open terrain where these air masses can meet across long distances. The front then becomes the organizing line of the weather pattern. It separates seasons in miniature, dividing air that still carries the character of late winter from air already behaving more like early summer. The atmosphere responds to this contrast with cloud formation, precipitation, wind shifts, and pressure changes that can stretch across large parts of the map. So in this seventh region, what is heading for the United States is no longer only a low-pressure system with moisture feeding into it. It is becoming organized through distinct boundaries where one air mass meets another. Cold fronts push and lift. Warm fronts glide and layer. Stationary fronts hold contrast in place. Across all of them, the atmosphere uses density, moisture, and convergence to convert broad movement into structured weather. The nation's changing pattern is now written onto the land in these long sloping lines of meeting air. Once the fronts have taken shape across the country, the atmosphere begins to produce one of its broadest visible expressions. Clouds gather into wide, connected shields, and rain spreads through large regions that may lie far from the narrowest boundaries or the most intense storms. This is the broad rain shield, a region where rising air is steady enough and deep enough to turn invisible moisture into layered cloud and widespread precipitation. In this eighth region, the weather over the United States becomes less a matter of abstract pressure lines and more a matter of sustained sky cover. persistent rain bands, and long hours in which the atmosphere releases the moisture that has been assembled and lifted. The pattern is often quieter in appearance than a line of violent thunderstorms, yet it can affect many more people across a much larger area. A broad rain shield forms when rising motion extends over a wide part of the atmosphere rather than remaining confined to narrow towers. Along and north of a warm front, for example, warm moist air glides up and over cooler, denser air near the surface. Because this ascent is gradual and expansive, the resulting clouds tend to form in layers. High thin clouds appear first, then thicker middle layers, and finally deeper low clouds capable of steady rain. Around a developing low-pressure system, this process can spread across several states. In other cases, a stationary boundary or an upper-level disturbance enhances the lifting over an already moist region, and the cloud shield grows wider and more persistent. In every case, the main process remains the same. Air is lifted over a large area, cooled into saturation, and kept rising long enough for precipitation to continue. This kind of rain often falls from nimbus stratus, a thick-layered cloud associated with continuous precipitation, though other cloud types can be mixed within the shield. The atmosphere does not separate itself into perfectly tidy categories. Embedded within the wider cloud field there may be narrower bands where lift is stronger, raindrops are larger, and rainfall becomes heavier for a time. Between these bands, the rain may lighten to drizzle or fine steady drops. What matters is that the whole region belongs to one connected structure. The sky remains overcast, the light grows muted, and the weather settles into duration rather than sudden violence. Roads remain wet for hours. Streams begin to respond. Soil absorbs what it can, and then more slowly begins to yield water onward. Meteorologists pay close attention to the depth of moisture in the atmospheric column during such events. A column is the full vertical slice of air above a place. If moist air extends through a deep layer rather than only near the surface, the atmosphere can sustain broader and more efficient precipitation. Lift acting on a shallow, moist layer may produce low clouds and patchy light rain. Lift acting on a deep moist column can produce a mature rain shield that persists through much of a day or night. Soundings from weather balloons help reveal this structure by showing how temperature and moisture change with height. When much of the column lies near saturation and the winds continue feeding air into the region of ascent, forecasters know that the broad shield is likely to endure. The character of the rain also depends on temperature through the cloud and below it. In many spring systems, the upper cloud contains ice crystals even while the lower levels remain above freezing. Precipitation may begin aloft as ice, then melt into raindrops as it falls through warmer air beneath. In other cases, the lower levels are cool enough that the rain reaches the ground cold and dense, helping reinforce the cooler side of the front. This feedback matters because precipitation itself can alter the local atmosphere. Evaporation below cloud can cool the air. Persistent rain can stabilize the lower layers and prevent rapid warming during the day. A broad rain shield therefore does not merely reflect the surrounding pattern, it also modifies that pattern, especially near the surface. Within the shield, wind usually shifts more gradually than it does along a sharp thunderstorm line. Pressure may continue falling or leveling off depending on the position relative to the low. Visibility can vary from fair to poor. Ceiling, which is the height of the lowest substantial cloud layer, often lowers as the denser part of the shield arrives. Aviation, road travel, and outdoor work are affected not because each raindrop is extreme, but because the weather becomes persistent and widespread. Fields may remain too wet for machinery. Urban drainage systems begin to fill. River basins collect runoff over many hours, especially if earlier rainfall has already left the ground saturated. Quiet weather can be consequential weather when it lasts. The broad rain shield often contains internal structure that is not immediately visible from the ground. Within the larger overcast area, small waves of stronger lift may travel along fronts or around the low-pressure center. These waves can create mesoscale bands, meaning features that are smaller than the full storm system but still large enough to cover counties or several states. Mesoscale simply refers to the middle scale between local and continental. In these bands, rainfall rates may increase noticeably. The cause can be frontogenesis, which is the strengthening of a frontal contrast, or deformation, which is the stretching and turning of air within the circulation that focuses cloud and precipitation into narrower zones. These terms may sound technical, but the effect is plain. A place beneath one of these embedded bands may receive much more rain than another location only a short distance away, even while both remain under the same broad shield. At times, the rain shield also serves as the outer envelope around more active convection farther south or closer to the cold front. The northern and eastern part of the system may remain dominated by layered clouds and steady rain, while the southern flank supports taller clouds and more vigorous showers. Yet in this eighth region of the story, the focus remains on the expansive shield itself, not on the storm cores that may exist elsewhere. This is the atmosphere in its sustained mode, releasing moisture over broad terrain through orderly ascent rather than through isolated explosive bursts. The emotional quality of such weather is often one of stillness, though the physics beneath it are active and continuous. Vapor condenses, droplets grow through collision, ice crystals form and melt. Winds at different levels keep transporting moisture into the region of lift. The cloud deck thickens where ascent persists and thins where sinking air begins to intrude. None of this stops simply because the rainfall seems gentle. The broad shield is a sign that the larger system is functioning efficiently across a wide area. It means the fronts are active, the moisture supply is established, and the atmosphere is able to convert invisible water vapor into long-lasting precipitation without needing dramatic local triggers. So in this eighth region, what is heading for the United States becomes a connected canopy of cloud and rain. It spreads beyond narrow boundaries and beyond the most intense storm corridors. It settles over the land as layered overcast, sustained ascent, and long hours of falling water. The weather pattern now reaches the ground over broad distances, not through sudden extremes alone, but through the steady release of moisture from a deeply organized sky. On the colder side of the weather system, the atmosphere tells a different story. Here the same moisture that falls as ordinary rain elsewhere meets air that is cold enough, deep enough, or layered in such a way that the precipitation changes form before it reaches the ground. In this ninth region, the warning over the United States moves into the cold margins of the pattern, where temperature through the lower atmosphere determines whether falling moisture arrives as snow, sleet, freezing rain, or cold rain. The physics is precise, yet the outcome can vary over surprisingly short distances. A slight difference in altitude, a shallow layer of cold air near the ground, or a small shift in the position of a front can separate wet roads from icy ones, or heavy rain from heavy snow. All precipitation begins aloft within cloud where water vapor condenses into droplets or deposits directly onto ice crystals. In colder clouds, ice often becomes the dominant form first. Snowflakes begin as ice crystals that grow as water vapor attaches to them. Their shape depends on temperature and moisture within the cloud, but the broader point is simple. The falling particle usually starts in a cold environment high above the ground. What happens next depends on the layers of air it passes through on the way down. If the entire column remains below freezing, the snow survives intact and reaches the surface as snow. If the flakes pass through a sufficiently deep layer of air above freezing, they melt into raindrops. If they then re-enter a layer of colder air near the surface, other outcomes become possible. Snow is often the most familiar cold-side precipitation. It forms when the air from cloud to ground stays cold enough to keep the ice crystals from melting. Yet even snow is not a single uniform thing. Large wet flakes often fall when the air is close to freezing and the cloud contains abundant moisture. Smaller, drier flakes are more common in colder air. Strong upward motion within the cloud can increase snowfall rates by producing more crystals and allowing them to grow efficiently. In broad winter-like shield precipitation north of a warm front or west of a deepening low, snow may fall steadily for many hours. During spring in the United States, this usually happens on the northern fringe of a storm system, where the cold reservoir remains deep enough for the rain shield to become a snow shield instead. Sleet forms when snowflakes melt partly or completely in a layer of warmer air aloft, then fall into a deeper sub-freezing layer closer to the ground and refreeze into small pellets of ice before reaching the surface. These pellets bounce when they land and can accumulate like a granular covering. Freezing rain forms through a different temperature structure. In that case, the snowflake melts fully into rain in a warm layer aloft, but the cold air near the surface is too shallow for the drop to refreeze in the air. The drop remains liquid but becomes supercooled, meaning it is still liquid below freezing. When it strikes a road, tree branch, power line, or bridge, it freezes on contact and creates glaze ice. This form of precipitation is especially dangerous because very little accumulation is needed to make travel hazardous and to place damaging weight on exposed surfaces. Meteorologists pay close attention to the vertical temperature profile during these events because surface temperature alone is not enough to determine precipitation type. A thermometer at ground level may read just above or just below freezing, yet a warm layer several hundred meters above the ground can completely alter what falls. Weather balloons provide direct measurements of this structure, while radar and model guidance help show how it may change through time. Forecasting the exact transition line between snow, sleet, freezing rain, and rain is one of the more delicate parts of weather prediction, particularly in spring when colder air often occupies only part of the lower atmosphere and is retreating or advancing at the same time the storm is evolving. Cold margins are also shaped by topography. Higher terrain cools more easily and may remain below freezing longer than surrounding lowlands. Valleys can trap shallow cold air, especially when dense air drains downslope and pools near the surface, in the Appalachians, parts of the interior northeast, the upper Midwest, or elevated western basins. Small changes in height can therefore produce very different conditions within a short distance. One road may remain wet while another becomes icy. One town may receive a heavy cold rain while a nearby ridge collects snow. The storm itself is broad, but the lower boundary between frozen and liquid precipitation can be very fine. The timing of cold air retreat or reinforcement matters as much as the temperature itself. If warmer air advances aloft while cold air remains trapped near the ground, the region of freezing rain may expand. If colder air deepens from the north, rain may change to sleet or snow. If the surface warms through the day while the upper pattern weakens, frozen precipitation may turn to rain and reduce the threat. Yet a late-day temperature rise does not always solve the problem. Ice already on untreated surfaces can linger. Meltwater can refreeze overnight if skies clear and colder air returns. Meteorologists therefore treat the cold side of a storm not as a static zone but as a moving layered structure, with hazards changing as the atmosphere slowly rearranges itself. Snow and ice on the cold margin also affect the broader system. Fresh snow reflects sunlight and keeps the surface cooler. Melting snow consumes energy and limits warming. Cold rain and evaporative cooling beneath a rain shield can help maintain a near-freezing surface layer longer than simple daytime heating might suggest. This means the precipitation itself can help preserve the conditions that allow it to remain frozen or freezing. The atmosphere and surface begin to interact in a quiet feedback. A place under steady precipitation may stay colder than nearby regions with lighter precipitation, simply because the ongoing melting and evaporation keep draining heat from the near-surface air. Visibility often deteriorates sharply in snow, especially when flakes are dense and winds increase around the pressure system. Roads can become slick from compaction, slush, or hidden ice beneath fresh accumulation. Freezing rain creates perhaps the most deceptive surface conditions, as pavement may appear merely wet while already coated with a thin frozen layer. Trees bend under the added weight. Power lines become vulnerable. Even when the cold margin occupies a smaller part of the national map than the broad rain shield or thunderstorm sector, it can still produce severe local disruption because its hazards are efficient and concentrated. So in this 9th region, the warning narrows into the atmosphere's cold edge, where the form of precipitation depends on the exact arrangement of temperature through depth rather than on moisture alone. Snow survives in a cold column. Sleet refreezes on the way down. Freezing rain waits until the moment of contact. Along this margin, the same storm that brings steady rain elsewhere becomes a problem of ice, slush, glaze, and cold accumulation, shaped by layers of air that are thin in distance yet decisive in effect. South of the colder margins and often east of the advancing cold front, the atmosphere enters a different state. Here the air is warmer, more humid, and more responsive to lifting. This is the thunderstorm country of the weather system, the part in which ordinary rising motion can deepen into towering clouds and organized convection. Convection is the vertical transport of heat and moisture through rising and sinking air. In this 10th region, the warning over the United States moves into the unstable sector, where the lower atmosphere contains the fuel for vigorous storms and where the interaction of moisture, warmth, lift, and wind can produce damaging weather over short periods of time. The warm sector usually lies between the retreating warm front to the north and the approaching cold front or dry boundary to the west. Within this corridor, southerly winds often continue bringing moisture inland from the Gulf, while daytime heating warms the ground beneath. The result is a lower atmosphere that becomes increasingly buoyant. Buoyancy is the tendency of an air parcel to rise when it becomes warmer and therefore less dense than the surrounding air. If that parcel is lifted enough to reach saturation, cloud forms. If it then remains warmer than the environment as it rises, it can continue climbing rapidly. The atmosphere has then crossed from simple cloud formation into convective development. Meteorologists describe this stored potential with a measure called convective available potential energy, often shortened in technical discussion to CAPE. It represents the amount of energy a rising parcel can use once it becomes positively buoyant. In plain terms, it reflects how much upward acceleration the atmosphere can support. A higher value does not guarantee severe weather, but it indicates that the atmosphere is more capable of building tall, vigorous storm clouds if the air is lifted through any stable layer near the surface. In spring across the United States, CAPE often grows where warm, humid air is present below colder air aloft, or where strong daytime heating acts on a moist boundary layer. The key idea is not the number itself, but the presence of an atmosphere ready to rise deeply once the process begins. That process usually needs a trigger. A cold front can provide one by forcing warm air upward. A dry line, which is a sharp boundary between moist and much drier air, can provide another outflow from older storms. subtle waves in the pressure field, or terrain effects may also begin the lift. Sometimes the atmosphere develops a cap, a layer of warmer air aloft that suppresses rising parcels for a time. This cap may delay storm formation through much of the day, even while warmth and moisture continue building below it. If the cap later weakens or the forcing becomes strong enough to break through it, storm development can begin quickly and sometimes explosively. The calm before storms in the warm sector is often not the absence of energy. It is the temporary holding of that energy beneath a restraining layer. Once deep convection begins, the cloud can grow into a cumulonimbus, the classic thunderstorm tower. Warm, moist air rises rapidly within the updraft, cools, condenses, and releases latent heat, which further strengthens the ascent higher in the cloud. Water droplets and ice particles interact in strong turbulent motion. Precipitation begins to form. Some of it is carried upward again by the updraft. Some falls outward and downward, dragging cooler air with it. This descending air forms the downdraft. A thunderstorm therefore contains both vigorous upward and downward motion, and its character depends on how these motions are arranged. If rain falls directly through the updraft too early, the storm may weaken quickly. If wind shear separates the updraft from the downdraft, the storm can persist longer and organize more efficiently. Wind shear is especially important in this region. It refers to changes in wind speed or direction with height, and it is often pronounced in spring over the United States because strong upper-level flow remains present above the warm, moist lower atmosphere. When shear is weak, storms may remain short-lived and scattered. When shear is stronger, storm cells can tilt, rotate, or merge into lines and clusters. A tilted storm keeps its updraft from being choked by its own falling rain. This allows the cloud to grow taller, last longer, and produce more substantial hazards. Under the right combination of instability and shear, storms can become supercells, which are thunderstorms with a persistent rotating updraft. Not every severe weather day produces them, but they represent one of the most organized and dangerous expressions of the unstable sector. Even when storms do not become isolated rotating cells, the warm sector can still support long lines of thunderstorms along cold fronts or prefrontal troughs. These lines may produce widespread damaging wind as downdrafts combine into a forward-moving surge of cooler air. Embedded stronger circulations may still develop within the line. In other settings, multiple storm clusters form through the evening and night as the low-level jet continues feeding warm, moist air into the boundary. Heavy rain, frequent lightning, hail, and sudden wind gusts become possible across a broad region. The unstable sector is therefore not one single storm mode. It is an atmospheric environment in which several organized forms of convection can emerge depending on the exact balance of lift, moisture, shear, and capping. Meteorologists also examine lapse rates, which describe how quickly temperature decreases with height. Steeper lapse rates mean the air cools rapidly aloft, increasing instability because a lifted parcel remains relatively warmer than its environment. Cold air associated with the upper trough moving above a warm, moist surface layer often steepens lapse rates and makes the warm sector more responsive to lifting. Surface heating adds to this effect during the day, especially where cloud cover is thin enough to allow strong sunshine. Yet too much early cloud or rain can limit heating and reduce instability locally. This is why severe weather forecasting often depends on subtle differences in cloud breaks, moisture depth, and boundary location across neighboring areas. At the ground, the approach of thunderstorm country may first be felt in small changes. The air grows heavier with moisture, wind from the south persists, the sky may become increasingly hazy or develop growing cumulus clouds by afternoon. Pressure may fall slowly. Farther west, towering clouds may appear near a front or dry line. Radar begins to reveal echoes where the first cells rise. Once storms mature, the hazards can escalate quickly. Large hail forms where strong updrafts keep ice suspended long enough to grow. Damaging wind develops where descending air accelerates toward the surface. Isolated tornadoes may form where rotation near the ground is strengthened along boundaries and drawn into a storm's updraft. Each of these hazards has its own detailed physics, but all begin with the same large truth. The warm sector has become unstable and organized enough to support deep convection. So in this 10th region, what is heading for the United States enters the part of the atmosphere where warnings often become most urgent and most localized. The broad pattern of pressure, moisture, and fronts has now prepared a corridor in which rising air can become storm towers. Warm, humid air provides fuel. Lift begins the ascent. Wind shear shapes the storm. The result is a landscape of thunderstorms capable of wind, hail, flooding rain, and in some cases tornadoes, all emerging from the unstable heart of the larger weather system. After the rain has formed in cloud and begun falling through the atmosphere, it meets the surface of the country, and a new part of the weather story begins. In this 11th region, the warning turns from rain in the air to water over the ground. What matters now is no longer only how much moisture condenses or how wide the cloud shield grows. What matters is how quickly water reaches the land, how easily the ground can absorb it, how efficiently streams and rivers can carry it away, and how strongly roads, fields, hillsides, drainage channels, and cities alter its movement. Flooding is not produced by rain alone. It emerges from the meeting between rainfall and landscape, between the amount of water arriving and the limited ways the surface can receive or release it. When rain first reaches dry soil, some of it infiltrates. Infiltration means the movement of water from the surface into the ground through pores and spaces between soil particles. If the soil is loose, relatively dry, and covered in vegetation, this process may be efficient for a time. Water enters, spreads downward, and partly replenishes soil moisture. But infiltration is not limitless. Different soils behave differently. Sandy ground often allows water to move through more readily. Clay-rich soil can absorb water more slowly because its particles are very small and packed tightly together. Frozen ground, compacted earth, or already saturated fields may accept very little additional water. In those cases, rainfall that cannot enter the ground becomes runoff, meaning water flowing across the surface. Runoff begins quietly. Small films of water gather on leaves, bare soil, pavement, and grass. They move downslope under gravity, following the smallest depressions and pathways. Separate threads merge into thin rivulets, then into shallow moving sheets, then into ditches, gullies, roadside channels, and storm drains. If rainfall continues, the process accelerates. The land surface begins to connect. Water that once fell in separate drops now behaves as a linked moving layer. This is one reason intense rainfall can transform a landscape so quickly. The change is not only about the amount of water, it is about the moment when scattered wetness becomes organized flow. Meteorologists pay close attention to rainfall rate in this part of the story. A moderate amount of rain spread over many hours may allow the land and streams to respond gradually. The same total amount falling in a short period can overwhelm infiltration and drainage. Flash flooding is the most rapid form of this problem. It occurs when heavy rain falls fast enough that small channels, urban surfaces, or steep terrain cannot carry it safely away. Water levels rise within minutes or a few hours. Roads disappear beneath muddy flow. Low crossings fill. Small creeks become powerful torrents. Dry washes in arid regions can turn dangerous with little warning because the rainfall may occur upstream and send a surge into normally quiet channels. Antecedent conditions, meaning the state of the land before the new rain begins, are often decisive. If soil is already wet from earlier storms, much less new rainfall is needed to produce runoff. Rivers already running high leave less room within their banks. Snowmelt may add water to the system even before fresh precipitation arrives. In agricultural regions, recently ploughed or compacted fields may shed water differently from ground covered by deep root systems. In forests, leaf litter and vegetation can slow runoff and encourage infiltration. Though steep slopes may still deliver large volumes downhill once rainfall becomes intense, every flood event therefore reflects both current rain and the memory of prior weather stored in the landscape. River flooding develops more slowly than flash flooding, but it can become broader and more prolonged. Streams gather water from tributaries, and tributaries gather water from smaller drainage basins. As rain falls over a wide region, these branching networks begin carrying the water toward larger channels. Even if the rain at one specific point is not especially intense, the combined effect across an entire basin can raise river levels steadily over many hours or days. Flood crests then move downstream, affecting communities far from the original heaviest rain. This is why broad rain shields can be as important to flood forecasting as intense thunderstorms. Long-duration rainfall over a large watershed can create major river flooding even without dramatic local downpours. Urban areas create their own version of this problem. Pavement, roofs, parking areas, and compacted ground allow very little infiltration. Water that might have soaked into soil instead runs quickly into gutters, drains, and low streets. If the drainage system is undersized, clogged, or already full, water accumulates rapidly. The city becomes a surface of fast response. Rainfall that might have caused minor ponding over open countryside can produce hazardous street flooding in a dense developed area. Underpasses, basements, transit corridors, and low intersections become vulnerable. The geometry of the built environment also matters. Curbs direct flow, walls trap it, and sloping roads can channel water into sudden concentrated streams. Topography sharpens these contrasts. Steep terrain speeds runoff and encourages rapid concentration in valleys below. Broad flat plains may allow water to spread more slowly, but across wider areas, especially where drainage gradients are weak. Along major rivers, floodplains exist because overflow has happened many times before. These low areas are part of the river system even when they remain dry in calmer weather. When rivers rise high enough, water returns to them, filling fields, forests, backwaters, and developed land built too low. Along coasts and tidal estuaries, heavy rainfall can become even more difficult to drain if elevated water levels downstream slow the river's ability to empty outward. The rain itself can change how the ground responds as an event continues. The first hour may soak into upper soil layers. The next hours begin filling those layers closer to saturation. After that, even less intense rainfall may produce greater runoff because the storage space in the ground has been reduced. This is one reason prolonged events often become more dangerous with time. The atmosphere may not intensify, but the land grows less able to cope. Meteorologists and hydrologists therefore study not only forecast rainfall totals, but the sequence of rain and the pace at which the landscape is likely to lose its capacity to absorb it. Flood warnings also depend on scale. A thunderstorm may flood a small basin while leaving nearby rivers unchanged. A broad shield of moderate rain may create little immediate urban danger, but raise major rivers several days later. Repeated storms over the same corridor can combine the worst features of both, producing rapid local flooding and then longer-lasting river impacts. In every case, the physical logic remains simple. Water falls faster than the surface and drainage network can process it. Once that threshold is crossed, the problem becomes one of movement over land, not only of weather in the sky. So in this 11th region, what is heading for the United States becomes a surface story of runoff, saturated soil, overflowing channels, and water seeking the lowest path. Rainfall meets terrain, pavement, rivers, and floodplains, and the consequences depend on how much can be absorbed, stored, and carried away. The warning has now reached the ground completely. It is no longer only about cloud and precipitation. It is about where the water goes after it falls. Away from the broad rain shield and beyond the most humid part of the thunderstorm sector, the same weather pattern can produce a very different hazard. In this 12th region, the atmosphere turns drier, the clouds thin or break, and the wind begins to matter in a new way. This is the fire weather side of the system, where strong air movement, low humidity, warm temperatures, and receptive vegetation combine to increase the risk that any spark may spread quickly across the land. The danger here does not come from falling water or deep saturated cloud. It comes from an atmosphere that draws moisture out of grasses, brush, and surface fuels while moving fast enough to push flames forward. Meteorologists watch this part of the pattern closely because the same pressure gradients and upper-level support that organize storms elsewhere can produce dangerous burning conditions over the southern plains, parts of the southwest, and other dry regions of the United States. Humidity is central to this hazard. When the air is dry, it can continue taking moisture from the ground, from plants, and from dead vegetation. Fine fuels such as grass, leaves, pine needles, and small twigs respond quickly to atmospheric dryness. They gain and lose moisture over short periods of time, after a humid night or recent rain. They may be less ready to ignite, but under strong sun, low humidity, and moving air, they dry rapidly. Meteorologists often describe this with relative humidity, which compares how much water vapor the air contains to how much it could contain at that temperature. When relative humidity falls low, especially during the warmest part of the day, fuels can become increasingly available to burn. The atmosphere is not creating the flame by itself, but it is preparing the surface to support it. The dry side of a weather system often forms west of the main moisture plume, and behind a surface low or advancing front. In these areas, the winds may strengthen as the pressure gradient tightens, while air descending from aloft warms and dries as it sinks. Descending air compresses under higher pressure near the ground, and that compression raises its temperature. Warmer air can hold more water vapor, so unless additional moisture is supplied, its relative humidity falls. This is one of the quiet but powerful ways the atmosphere can create fire danger. It does not always need extreme heat in an absolute sense. It needs air that is dry relative to its temperature and moving briskly across a landscape with burnable fuels. Wind changes the problem from ignition to spread. A small flame in still air may remain localized. The same flame in strong wind leans forward, preheats fuel ahead of it, and spreads more rapidly. Wind also carries embers, which can start new fires downwind. These spot fires allow a fire to cross roads, dry channels, or breaks in vegetation that might otherwise slow it. Over open country, Wind can drive a grass fire with startling speed because the flames remain close to the surface, fuels, and the supply of oxygen is constantly renewed. In wooded or brush-covered terrain, strong gusts can produce erratic behavior, especially where slopes and canyons redirect the airflow. Meteorologists therefore treat wind as more than a simple background condition. It is often the main reason a day becomes critical rather than merely dry. The position of this dry windy sector within the larger weather pattern is often easy to understand in broad terms. East of the low and fronts, moisture may be increasing and clouds thickening. Farther west or southwest, drier air wraps into the system or spreads out ahead of a trough over elevated terrain. In the southern plains, this can happen when a dry line sharpens between moist Gulf air to the east and hot, dry continental air to the west. On the dry side of that boundary, skies may remain clearer, mixing during the day may extend deeply upward, and stronger winds from aloft may be transported down to the surface. Mixing means the exchange of air between the ground and the lower atmosphere through daytime heating and turbulence. When mixing is strong, dry air from above can be brought downward, further lowering humidity near the surface and increasing gusts. Vegetation determines how the atmospheric danger expresses itself. Lush green plants contain more moisture and are generally harder to ignite than cured grasses, drought-stressed brush, or dead leaf litter. Seasonal timing matters. In many parts of the central and western United States, early spring can be especially sensitive because new green growth is incomplete, while old grasses from the previous season remain dry and abundant. A windy dry day arriving after several rain-free days may therefore create an environment in which ignition becomes much easier. If a drought has persisted, larger fuels such as branches and shrubs may also be unusually dry. Yet even without prolonged drought, fine fuels alone can support fast-moving fire when humidity is low and winds are strong. Cloud cover also influences the fire weather environment. Thick clouds and rain-cooled air suppress surface heating, but on the dry side of the system the sky may remain partly clear or hazy, allowing stronger sunlight to warm the ground. As the surface warms, the air above it becomes more turbulent. This deepens the mixed layer and often strengthens afternoon wind gusts. Relative humidity usually falls toward its daily minimum during the same period. The overlap of strongest wind, warmest temperatures, and driest air often occurs in the afternoon and early evening. This timing is one reason fire weather alerts are commonly focused on that part of the day, even when winds remain breezy for much longer. Topography can make this hazard more uneven and more dangerous. On ridges and exposed plains, winds may remain stronger and steadier. In valleys, local channeling can accelerate the flow in one direction. Downslope winds warm and dry as they descend, sometimes sharply reducing humidity over short distances. On the lee side of mountains, descending air can also become turbulent and gusty. The atmosphere therefore interacts with the land in ways that make some corridors far more vulnerable than neighbouring ones. A forecast region may include both relatively modest fire spread potential and highly critical pockets shaped by terrain and vegetation together. Human activity often supplies the ignition source. Power equipment, vehicles, agricultural burning, discarded cigarettes, downed power lines, and accidental sparks can all begin fires when the atmospheric conditions are favourable. Lightning from dry thunderstorms can do the same, especially where rain evaporates before reaching the ground. Yet the meteorological warning focuses on the environment rather than on the cause of ignition. It asks a simpler question. If a fire starts today, how readily will the atmosphere help it grow and spread? On the dry, windy side of a major system, the answer can become troubling even without extraordinary heat. So in this 12th region, what is heading for the United States is not always water, cloud, or ice. In some areas it is the opposite, a dry moving atmosphere that strips moisture from fuels and pushes fire across the land. Strong pressure gradients, descending air, deep daytime mixing, and low humidity work together to create a landscape where ignition can turn quickly into fast spread. The larger weather pattern now reveals one of its sharpest contrasts. While some regions receive soaking rain and swollen rivers, others face wind, dryness, and the risk of flame. As the large weather pattern reaches the ground in full, it no longer behaves in exactly the same way everywhere. The broad circulation may be continental, the fronts may stretch across many states, and the moisture transport may come from far beyond the horizon. Yet the final expression of wind, rain, temperature, and storm structure is always altered by the land beneath. In this 13th region, the story turns to coastal and local modifiers, the features of the surface that reshape incoming weather once it arrives. Coastlines, hills, plains, forests, river valleys, lakes, and cities do not create the larger atmospheric pattern by themselves, but they bend it, slow it, sharpen it, or redistribute it. Meteorologists watch these local influences carefully because they explain why the same warning can feel different from one county to the next, even under the same broad system. Coastlines are among the clearest of these modifiers. Land warms and cools more quickly than water, so the air above land and the air above nearby ocean or gulf often differ in temperature and density. During the day, especially when sunshine is present between larger cloud bands, land may warm enough to create a local sea breeze. A sea breeze is a circulation in which cooler marine air moves inland near the surface, while warmer air over land rises and is replaced. During the night or under strong synoptic flow, meaning the larger scale background wind pattern, this local breeze may weaken or reverse. Yet even when the larger weather system dominates, coastal boundaries can still matter. They can sharpen temperature differences, concentrate moisture, and create narrow zones of convergence where showers and thunderstorms become more likely. A broad front approaching the Gulf Coast or the Atlantic seaboard may therefore interact with these local marine boundaries and produce more uneven rainfall or stronger storms than the large-scale map alone might suggest. Marine air also changes the character of rain and cloud near the coast, because water temperatures change more slowly than land temperatures. Coastal zones can remain cooler beneath onshore flow, while inland locations warm more rapidly. This may stabilize the lowest part of the atmosphere near the shore, reducing storm intensity there while allowing stronger development farther inland. In other cases, warm, moist marine air moving over cooler shelf waters can produce fog or low cloud that lingers even as brighter skies appear inland. The same moisture source that helps feed thunderstorms farther from the coast can therefore produce a calmer, dimmer, more layered sky right along the shoreline. Meteorologists must account for these differences because warnings for strong wind, flooding rain, or isolated severe storms often depend on where the inland advance of marine air meets the stronger heating over land. Mountains and hills alter the pattern through elevation and forced lifting. When moving air encounters rising terrain, it is pushed upward. Rising air cools, and if enough moisture is present, cloud and precipitation increase. This process can make windward slopes wetter than surrounding lowlands. On the opposite side of the terrain, descending air warms and dries, sometimes sharply. The result is a rain shadow, a region of reduced precipitation downwind of mountains. Yet the effect is not limited to rainfall totals. Terrain also bends airflow into channels, ridges, and wakes. A valley may guide strong wind along its length. A ridge may expose one community to powerful gusts while another just below remains comparatively sheltered. Cold air may drain downslope at night and pool in lower ground, preserving a chill long after nearby uplands have begun to warm. These local motions can change precipitation type, storm intensity, and flood behavior across short distances. The broad plains of the central United States create a different kind of modifier. Their relative openness allows low-level air masses to move with fewer interruptions, which is one reason large frontal systems and moisture surges can spread efficiently there. Yet even plains are not uniform. Subtle rises in elevation, dry riverbeds, vegetation differences, and soil moisture variations can influence surface temperature and humidity. On a spring day, one area may warm faster because cloud cover breaks earlier. Another may remain cooler due to morning rain or lingering low stratus. Those differences can sharpen local boundaries within the broader warm sector. Such boundaries may become focus zones for thunderstorm initiation because they gather wind and temperature contrast on a smaller scale. In this way, even gently rolling land can contribute to where deep convection begins. Large lakes also modify weather by acting as inland water bodies with their own thermal influence. In spring, lake water is often cooler than nearby land, especially after sunny days begin warming the surface more strongly inland. Air moving across the lakes may cool and stabilize before reaching shore. Local lake breezes can then form, much like sea breezes, pushing cooler air inland and creating narrow convergence zones where showers may intensify. On the colder side of a storm, lakes may also add moisture to chilly air passing overhead, enhancing cloudiness or localized snow showers if the air is cold enough. Their presence therefore makes nearby weather less uniform and often more sensitive to wind direction than inland areas farther away. Forests, croplands, and bare ground each exchange heat and moisture with the atmosphere differently. Vegetation cools the surface partly through evapotranspiration, the transfer of water vapor from soil and plant surfaces into the air. Where the ground is moist and plants are active, afternoon temperatures may rise more slowly than over dry bare soil or dense built surfaces. A recently wetted agricultural region may therefore feel and behave differently from a dry field nearby under the same sun and wind. These contrasts can influence the depth of mixing, the humidity near the ground, and the readiness of the air to support strong gusts or convective development. They are subtle compared with fronts, yet at the local scale they help decide how the broader pattern is expressed. Cities produce one of the most familiar local modifiers. Urban materials such as concrete, asphalt, and brick absorb and store heat more effectively than many natural surfaces. Buildings also alter wind through friction, channeling, and turbulence. The result is an urban heat island, a tendency for city centres and dense developed zones to remain warmer than surrounding rural areas, especially at night. This added warmth can weaken frost, deepen local mixing, and in some cases help maintain slightly more buoyant air. Urban surfaces also reduce infiltration, making heavy rainfall more likely to become rapid street flooding. Wind between tall buildings may accelerate in one corridor while slowing in another. Rainfall runoff reaches drains quickly, and if those drains fill, the city's built geometry can trap water in low points. So the urban landscape reshapes both the thermal and hydrological parts of the warning at once. Local modifiers also interact with one another. A coastal city near hilly terrain may experience marine cooling at the shoreline, channeled wind in valleys, urban warmth after sunset, and poor drainage in paved low districts all within the same weather event. A storm line approaching such a place does not encounter a simple surface. It encounters a mosaic of thermal, mechanical, and hydrological influences. Meteorologists therefore refine forecasts with local knowledge, radar, satellite observations, surface stations, and high-resolution models. They know that the larger pattern explains the general risk, but the ground determines many of the details. So in this 13th region, what is heading for the United States no longer arrives on a blank surface. It meets coastlines that cool and converge, hills that lift and channel, plains that allow boundaries to sharpen, lakes that stabilize and focus, vegetation that exchanges moisture, and cities that warm, redirect wind, and flood quickly. The atmosphere is now being rewritten by the land beneath it. The warning remains part of one broad system, but its final shape grows increasingly local as geography begins to speak through the weather. Within the broad thunderstorm sector, after moisture, instability, and lift have aligned, the atmosphere can build individual storm towers that behave like complex vertical engines. In this 14th region, the story moves inward from the larger warm sector into the structure of the storm cell itself. What has so far been described in terms of fronts, pressure, humidity, and regional instability now becomes concentrated inside a single deep cloud. Here the motions are no longer spread gently across states or river basins. They rise and sink within a comparatively narrow column, carrying heat, water, and ice through several kilometers of atmosphere in a short span of time. Meteorologists study this interior carefully because many of the hazards that seem sudden at the ground begin as ordered physical processes inside the storm. A thunderstorm cell begins when a parcel of warm, moist air is lifted high enough to reach saturation and then becomes more buoyant than the air around it. Once this happens, the parcel continues rising as an updraft. The updraft is the storm's central rising current, and it is the defining feature of deep convection. Inside it, air can move upward at remarkable speed, though the exact speed depends on instability, moisture, and how well the storm is organized. As the air rises, pressure decreases. The rising air expands and cools. Water vapor condenses into tiny droplets, forming visible cloud. The condensation releases latent heat, which makes the rising air relatively warmer than its surroundings and helps it keep climbing. In this way, the updraft strengthens itself for a time through the very cloud formation it produces. The growing cloud soon reaches levels cold enough for ice to form. Above the freezing level, droplets may remain liquid even below freezing for a time. These are supercooled droplets, and they are important because they can freeze onto ice particles and contribute to hail growth. Higher in the storm, ice crystals, grapple, hail embryos, and liquid droplets exist together in turbulent motion. Grapple is a soft pellet of ice formed when supercooled droplets freeze onto a snow crystal. This mixed region of water and ice is one of the most active parts of the storm. Here particles collide, freeze, melt, and separate under strong vertical currents. The thunderstorm is no longer only a cloud of droplets. It becomes a layered and restless system of phase changes, with water moving repeatedly between vapor, liquid, and ice. Not all of the condensed water remains suspended. As droplets merge through collision and coalescence, they become large enough to begin falling. Ice particles also grow until gravity overcomes the upward push of the rising air. Precipitation then starts descending through the cloud. Some of it still falls through the updraft and may be carried upward again. Some of it enters neighboring air and begins the downdraft. A downdraft is a descending current produced when air is cooled and dragged downward by rain, melting hail, or evaporation. Evaporation absorbs heat, cooling the air and making it denser. Dense air sinks. When enough cooling occurs, the descending air accelerates and becomes a significant part of the storm's internal circulation. The relationship between updraft and downdraft determines much of the storm's life cycle. In a weak and poorly organized cell, falling rain may quickly collapse into the same area where the updraft is trying to rise. The cool downdraft then undercuts the warm inflow, and the storm weakens. In a stronger and more organized cell, wind shear tilts the storm so that the updraft and downdraft are separated in space. This allows warm, moist inflow to continue entering the updraft while rain and cooled air fall away on one side. The storm can then persist longer, sometimes much longer, because it is not immediately destroying its own fuel source. The internal architecture becomes more stable even while the motions remain violent. Hail forms when ice particles are held aloft inside strong updrafts, long enough to grow through repeated encounters with supercooled droplets. A small ice embryo may rise, collect a layer of frozen water, begin falling, then be lifted again and gather more ice. The final stone records these repeated journeys in layers, much as a tree records growth in rings. The stronger the updraft, the longer the stone can remain suspended and the larger it can become before it finally falls. Large hail is therefore a sign not merely of cold air aloft, but of a storm whose rising current is powerful enough to support repeated growth cycles within the mixed phase region of the cloud. Electrical charge also develops in this same interior zone. Thunderstorms become electrified because collisions between ice particles of different sizes help separate charge within the cloud. The exact microphysical details remain an active field of research, but observations show a consistent broad outcome. Different parts of the cloud acquire different charge regions, often with negative charge concentrated in the middle levels and positive charge above and sometimes below. Once the electric field becomes strong enough, a discharge occurs. Lightning is the visible result of the atmosphere rapidly equalizing that imbalance. Thunder follows because the lightning channel heats the surrounding air so suddenly that the air expands explosively, creating a shock wave that travels outward as sound. The flash and the sound therefore begin in the storm's inner charge structure, long before they become a human experience at the ground. The descending air in a thunderstorm eventually spreads outward when it reaches the surface. This forms an outflow boundary, a shallow pool of cooler air moving away from the storm. The leading edge of this pool can lift warm, moist air ahead of it, and sometimes trigger new cells nearby. Inside the storm. This means the downdraft does not simply end when it reaches the ground. It reshapes the environment around the cell and can influence whether the storm line grows, weakens, or propagates forward. In organized systems, especially lines of storms, many downdrafts can merge into a stronger collective cold pool that drives new ascent along its leading edge. Rotation may also develop inside a storm when wind shear causes the horizontal spin already present in the environment to be tilted into the vertical by the updraft. If the updraft stretches that rotating air column, the rotation can intensify. In a supercell, this creates a mesocyclone, a persistent rotating updraft on the scale of the storm itself. Not every rotating storm produces a tornado, and not every severe storm rotates strongly, but the possibility begins here in the storm cell's internal geometry. The broader environment provides the shear, but the cell must convert that shear into a structured rotating updraft for the process to matter at smaller scales. So in this 14th region, what is heading toward the ground is first assembled inside the storm tower. Warm moist inflow rises as the updraft. Water condenses and ice forms. Precipitation begins to fall, and cool air descends as the downdraft. Hail grows through repeated freezing. Lightning emerges from charge separation among ice particles. Rotation may strengthen if the wind structure supports it. The storm cell is therefore not a simple cloud. It is a deep internal machine, turning atmospheric contrast into falling rain, hail, electrical discharge, and concentrated wind through the continuous exchange of rising and sinking air. At the finest inner scale of the weather, the broad pattern disappears into details so small that they cannot be seen directly from the ground. Yet these details help decide how the warning is ultimately lived. In this 15th region, the story reaches the smallest motions inside cloud: rain shaft, gust front, and near-surface air. Here the atmosphere becomes a world of droplets, ice crystals, turbulence, pressure jumps, and sudden local shifts in wind. A storm that has already been shaped by continents, pressure systems, fronts, moisture transport, and organized cloud structure now expresses itself through microphysics and short-lived motions measured in seconds, meters, and tiny changes of temperature and pressure. This is the level at which a raindrop forms. A hailstone acquires its final layer, a gust arrives at one street corner before another, and a warning becomes immediate human weather. Inside cloud, not every droplet is the same size. Some begin on microscopic particles called aerosols, tiny bits of salt, dust, smoke, or other material suspended in the air. Water vapor condenses onto these particles when the air reaches saturation, creating cloud droplets. At first, the droplets are extremely small, so small that they can remain suspended by weak upward motions. A visible cloud is therefore not heavy rain waiting to fall. It is a suspension of countless tiny droplets or ice crystals held aloft by the moving air. For precipitation to reach the ground, these particles must grow. In warm cloud, droplets collide and merge, a process called collision coalescence. In colder cloud, ice crystals may grow at the expense of nearby supercooled droplets, because water vapor is more readily deposited onto ice. These growth pathways determine whether precipitation begins efficiently or slowly, and whether the cloud yields drizzle, steady rain, wet snow, or mixed frozen particles. The shapes of ice crystals matter. Temperature and humidity in the cloud influence whether a crystal grows as a plate, column, needle, or branching dendrite. Dendrites are star-like crystals with delicate branching arms, common in colder cloud layers with abundant moisture. When many such crystals gather and stick together, snowfall can become fluffy and efficient. In other temperature ranges, crystals may remain simpler and denser, producing a different texture of snow. These small structural differences affect how quickly particles fall, how readily they collect liquid water, and how tightly they pack once they reach the ground. A winter margin of the storm therefore owes part of its character to crystal geometry too small for ordinary sight. Raindrops also have a natural limit to their shape. Small ones remain nearly spherical because surface tension holds them together. Larger drops flatten underneath as air resistance acts on them during descent. If they become too large, they become unstable and break apart into smaller drops. Rainfall intensity is therefore not only a matter of how many drops are falling, but also how the distribution of drop sizes evolves inside the cloud. Radar can infer some of this structure indirectly, because different sizes and phases of precipitation scatter energy in different ways. To a person at the ground, this fine structure is felt as the difference between mist, soft steady rain, large cold drops before a storm core, or the hard mixed impacts of hail and rain together. Turbulence works continuously through all of this. Turbulence is irregular swirling motion, the opposite of smooth laminar flow. Inside a storm it mixes air of different temperature and moisture, alters droplet collisions, bends precipitation shafts, and changes how momentum is transported downward from stronger winds aloft. Near the surface, turbulence may intensify when rain-cooled air spreads outward as a gust front. A gust front is the leading edge of air pushed outward by a storm's downdraft. It may arrive as a sudden wind shift, a brief temperature drop, a burst of dust, or a line of low cloud. On one street, the wind may surge first because of building arrangement or tree cover. In an open field, the same boundary may race forward with little resistance. The gust itself is part of the storm, but its exact expression is shaped by tiny eddies, rough surfaces, and the local layout of the land. Pressure can change on these scales as well. A strong downdraft spreading at the surface may produce a small but noticeable pressure jump. The air becomes cooler and denser, and the wind arrives with a more forceful edge. In very intense downdrafts, localized bursts of sinking air can strike the ground and spread outward rapidly, producing damaging straight-line wind. These bursts are called downbursts. A downburst may affect only a limited area, but within that area its winds can be severe. Its formation depends on fine-scale processes within the storm, including evaporation, melting, precipitation loading, and how the descending air interacts with the air beneath it. The broad environment matters, but the final outcome depends on these concentrated inner motions. Lightning at this smallest lived scale is not only charge separation inside cloud, but the final stepped connection between cloud and ground or between charged regions within the storm. The exact path is irregular, branching through the air in a rapid sequence of conductive steps. When connection is made, the return stroke travels with extraordinary speed and brilliance. The surrounding air is heated intensely and almost instantly. Thunder then rolls outward through layers of air that may reflect, absorb, or delay the sound, which is why it sometimes cracks sharply and at other times rumbles for many seconds. Even this familiar sensation depends on local structure and temperature, humidity, terrain, and cloud height. Very near the ground, rain, hail, wind, and temperature change interact with ordinary surfaces in immediate ways. A warm road may melt small hail briefly before accumulation begins. A thin, cold surface layer may allow freezing rain to glaze a bridge before nearby pavement ices over. Saturated soil may fail on a slope once runoff concentrates into one channel. Visibility can collapse not only because precipitation intensifies overhead, but because droplets of a certain size scatter light more efficiently, or because wind lifts dust ahead of the storm. These are the final expressions of the atmosphere's layered processes. They are local, transient, and deeply physical. At this inner scale, uncertainty also becomes greatest. Meteorologists can identify the broad pattern, the frontal boundaries, the moisture field, and the unstable sector with increasing confidence. But the precise location of one hail core, one narrow corridor of damaging wind, or one abrupt flood response may still depend on interactions too fine to resolve perfectly in advance. Observations indicate the environment in which such features are likely. It remains uncertain exactly where each smallest outcome will emerge until the storm begins expressing its internal structure in real time. That uncertainty is not failure. It is reflection of how the atmosphere behaves when very small processes finally govern the last step between forecast pattern and lived experience. So in this 15th region, what is heading for the United States reaches its most intimate form. Droplets condense on tiny particles. Ice crystals branch, collect, melt, or refreeze. Turbulence mixes momentum and moisture through irregular swirls. Gust fronts, pressure jumps, downbursts, lightning channels, and abrupt surface changes transform a continental warning into immediate local weather. The atmosphere has moved from planetary contrast to the smallest motions inside falling water and moving air. At that final inner scale, the warning is no longer abstract at all. It is the exact shape of rain on a window, wind at a doorway, ice on a branch, and pressure in the air just before the storm passes. The atmosphere gradually settles after the warning has passed through its many layers of motion. The broad currents continue over the continent, but at the ground the sharper edges begin to soften. Rain weakens into lighter drops, then into mist, then into damp stillness on roads, leaves, and roofs. Rivers continue their slow response where water has gathered, while elsewhere the land begins to release what it has absorbed back into the quieter air. In the colder margins, ice loosens its hold by degrees, or else remains for a time as a thin reminder of how precisely the atmosphere arranged its layers. In the drier regions, wind eases, and the grasses return to waiting beneath a calmer sky. What seemed at first like one warning has always been many connected processes moving inward from the largest scale to the smallest. Planetary contrast shapes the continent. Ocean moisture and northern cold define the outer supply. The high current aloft bends into troughs and ridges. Pressure responds below. Moisture returns from the south. Fronts take form. Rain spreads through broad cloud. Snow and ice gather on the cold edge. Storm towers rise in the unstable air. Water runs across the land. Dry wind hardens the fireweather side. Coast, hill, city, and valley reshape the whole pattern. Inside the storm, droplets, ice, charge, and turbulence complete the work. By the time the weather is felt on skin, glass, soil, and pavement, it has already passed through an immense chain of causes. Nothing in that chain is hurried, even when the local change seems sudden. The atmosphere is always moving energy, moisture, and mass from one place to another, arranging them into forms that can be mapped, measured, and slowly understood. Then the sharper motions fade, the clouds thin, the pressure steadies, air that was rising begins to rest. The country remains beneath the same sky, but the warning has become memory, carried away in the continuing flow above.